Combining ratios. Sometimes between different subgroups in a collection, a problem will give separately expressed ratios. So we'll have two or more ratios, and we'll have to relate these either to the whole or to absolute quantities. Before we begin, a few reminders. First of all, we typically write ratios as fractions, and one consequence of that is that we can write them as equivalent ratios, that is to say equivalent fractions. We know that 1/2 equals 5/10 or 10/20 or something like that. And so there might be times that we need to either simplify a ratio or to make it bigger in order to reconcile it with another ratio. Another trick is that we can use algebra. Suppose we have a ratio, say A to B equals 3 to 8. And that means that we can say that for some value of n, some unknown value of n, A equals 3n and B equals 8n. And therefore I can set up all kinds of algebraic equations, and then if I solve for n, I know the number of everything. As soon as I get the value of n, I know the number of everything. That's the advantage of using algebra with ratios. And finally, there's the very tricky issue of what we can and can't cancel in proportions. And so in a proportion, first of all, it's totally legal to cancel up and down. It's totally legal to cancel across two numerators or cancel across two denominators. Those are perfectly fine. Put happy faces there. But cross-canceling, that is always incorrect. Now, if this is news to you, if this is a new idea, please watch the lesson video, Operations with Proportions, in which I explain in detail which types of canceling you can do in a proportion and which types of canceling you can't do in a proportion. I'll assume you know all that in this video. The combining ratio scenario occurs when we are given two or more separate ratios within a larger group. Say in a group with type 1 and type 2, type 3 members, we might be given one ratio for type 1 to type 2 and a whole other ratio for type 2 to type 3. We have two basic strategies for approaching such questions. One strategy would be to find equivalent ratios. So for example, a ratio of 1 to 2 is equivalent to 7 to 14 or 13 to 26. And we'd adjust the equivalent ratios so that the common term, the one that corresponds to the same category in the two different ratios, is represented by the same number. So that's one strategy. Another strategy, if we have some absolute quantity, would be to either solve the ratio completely and use numbers, or to set up something algebraic and work with algebra. And so we have a few different approaches here that we're going to demonstrate in the few practice problems we have here. Here's practice problem number 1. Pause the video and see if you can solve this on your own. Okay. A certain high school team has only sophomores, juniors, and seniors. The ratio of sophomores to juniors is 2 to 3, and the ratio of juniors to seniors is 5 to 6. Sophomores are what fraction of the whole team? So here we have these two ratios, and the strategy we're going to use is to identify the common element, juniors. So juniors appear in both ratios, and so we're going to adjust the ratios so the number representing juniors is the same. So in the top ratio, juniors are represented by 3. In the bottom ratio, juniors are represented by 5. And so 3 and 5, the least common multiple is 15. We're going to get there by multiplying the top ratio, top and bottom, by 5, the bottom ratio, top and bottom, by 3. So those are our equivalent ratios. Now that juniors are represented by the same number in both ratios, we can combine the ratios. So now sophomores to juniors to seniors are 10 to 15 to 18. We can't simplify that. There's no single factor that is shared by all three of those numbers. No single factor bigger than 1. So we can't simplify that. But that is the overall ratio of sophomores to juniors to seniors. Well, now, if sophomores are 10 parts, juniors are 15 parts, and seniors are 18 parts, the whole is 43 parts. And so sophomores are 10/43 of the whole. Here's a second practice problem. Pause the video and then we'll talk about this. Okay, this problem is also a little bit on the easy side, perhaps a little bit easier than you'd see on the test, or one of the easiest possible things you'd see on the test. In a certain company, the ratio of programmers to marketers is 3:8, and the ratio of customer service reps to marketers is 2:3. There are 27 programmers. How many customer service reps? Well, here, of course, we could find equivalent ratios, but also we're given a number. So the strategy we're going to use, we can simply find the absolute quantity for each term one at a time. So we're given the number of programmers, and the only ratio with programmers is programmers to marketers. So we're going to have to use this to find the number of marketers. So 3:8 equals 27 to m. We're going to use the cancellation trick. We have a proportion. We're going to cancel across the numerators. Divide both numerators in that proportion by 3. Simplifies to a 1 and a 9. And now that we're down to 1, we can just cross multiply. So 1 times m equals 9 times 8, which is 72. So there are 72 marketers. Now that we know the number of marketers, we can figure out the number of customer service reps, because that ratio is 2:3. So we have 2/3 equals c over 72. Here we're going to divide both denominators by 3. So 24, so 72 divided by 3 is 24. We'll cross multiply here, and the number of customer service reps is 48, and that's the answer. Now here's a harder practice problem. This one takes a few more steps to tackle. Pause the video and then we'll talk about this. Okay, 1 cup of butter is enough for 8 of Roger's cookies, and 1 cup of sugar is enough for 5 of Roger's cookies. He uses 15 more cups of sugar than of butter. How many cookies did he make? Well, we're going to have to do a few different things here. Here we're going to have to combine the ratios, combine the two approaches. First, finding a single ratio that includes all 3 elements, and once we have that single ratio, then using the parts to get algebraic expressions for the 3 elements. So part 1, combining the ratios. We know butter to cookies 1 to 8. We know sugar to cookies 1 to 5. The common term here are cookies, and so the least common multiple of 8 and 5 is 40. So we're going to multiply the top ratio by 5 over 5, multiply the bottom ratio by 8 over 8. Now we can put everything together in one big ratio. Butter to sugar to cookies, 5 to 8 to 40. Now with that combined ratio, use algebra. So there's our combined ratio, and we're going to say for some n, and n just represents kind of an abstract part. For some n, the number of cups of butter would be 5n, the number of cups of sugar would be 8n, and the number of cookies would be 40n. And so we get this directly from that combined ratio. All right, now we can use that last piece of information. He used 15 more cups of sugar than of butter. That's a real word problem piece of information. So cups of sugar was 15 more than cups of butter, is what we're saying. Or in other words, cups of sugar is cups of butter plus 15. Or cups of sugar minus cups of butter equals 15. These are a few different ways to say the same thing. And this type of thinking, we're going to cover this type of thinking more in the word problem section, but this is just a preview of it. So we have 15 equals cups of sugar minus cups of butter. Well, we have algebraic expressions for these. Cups of sugar is 8n. We said that a few slides ago. Cups of butter is 5n. We have two algebraic expressions for these. Well, now we can just do algebra with this equation we have. Of course, 8n minus 5n is 3n. Divide by 3, we get n equals 5. Well, now we know the value of n, so now we can plug in and find all the absolute values. What we're looking for is the number of cookies. Number of cookies is 40n. Plug in 40 times 5, 200. We made 200 cookies. In summary, one method is to find equivalents so that common terms are equal in both ratios, then we can combine into one big ratio. Another method, if possible, solve for an individual value and use the ratios to solve for each additional individual values. And notice that in some problems we actually can solve in a few different ways, and in fact that's wonderful. You really understand a problem very well if you can take two entirely different approaches to it and get the right answer both times. That's always a good thing in your practice.